What we are going to do this week is basically as a continuation from the last week that we have coded NP neuron and the perceptron in the Python. So we will discuss that first because there's some part of the code which is written not being explained, and some hyperparameter introduction of some hyperparameter. So that is something we are going to discuss today. Followed by, that's the first half of the session by 7 if we can finish that quickly. In the second half, we're going to take a look at the sigmoid neuron from the theoretical perspective, because because it's a building block for all the next upcoming deep learning neurons that deep learning networks you're going to learn about, right? The back propagation, feed forward, and all that. So and from the next week, we will directly jump for the back propagation, feed forward networks, and all the the practical aspect, how to build that, and all those aspects we are going to see, and how to tweak the parameters, and all the practical aspect we will try to see from that onwards, and follow in between we will see the assignment questions. Because the reason why sigmoid neuron is important is, uh, from this point of onward, you will be seeing something called non-linear functions. So that is, again, it's important to reiterate that before going directly applying propagation. And since the maths will be very intensive, we might look at I might not do the whole derivation, but I will give you some intuition of what this mathematical intuition will tell about, and with this sigmoid neuron. Okay, so first let's come to the first part. So let me share the screen. Okay, let me share the entire screen. That will be better. And if you have any questions during this, please type down the chat. After that, once the expression is over, I will look into that. Okay, before that, let me share this again for the new people who have joined this time. So let me again share this Google Colab notebook where we have written the code last time. Okay, share in the chat. Okay, so just to give a summary before going towards the perceptron learning algorithm and how we did that. So just give again a recap kind of thing what we have done. Okay, so what we have done is, our aim at the was to build a simple MP neuron and a perceptron model using Python. To do that, we need a data. So for that data, we are directly importing with something called a sklearn dataset. Okay, now from sklearn dataset, we have extracted a breast cancer dataset using a load breast cancer function. Now, before jumping and try to learn a model, first we need to understand that what the dataset is all about. So we did certain pre-processing operation and certain operation which help us understand what the data look like. So if we just look at the raw data, it will something look like this. So x is, which is some typically called as input, will have some value within 1.79, some floating point values there, and the y is basically a simple two class value, that is either 0 and 1, that is whether breast cancer is there or not as of now. Okay, now using shape we get to know that instances of x and y, that is to know that how many rows and how many columns are there. So whenever we say columns, you are now you assume that columns means features of the data set. Okay, so when we are saying 30 columns, it means 30 features are present in the data set, and 569 instances are there. So maybe for one person, all these 30 features has been recorded. So likewise for 569 persons, the same 30 feature has been recorded. Now to visualize the data, you can use a pandas a library, and you can use a data frame, and you can visualize the data like this, where you can just get an idea of like what the data will look like. Okay, now that being said, we can also identify what the target variable, which is the y in this case, will look like. So in this case, this is a malignant and benign breast cancer. So so we can get this target name as well if you're not able to get it from the pandas, from direct visualization of the data. Now what we have done, after once we analyze the data and we get some understanding of what the data look like, we did it, we started doing the train test split, that is what percentage of the data should be on training and what percentage of data should be in the testing. So while doing this, we use the train test split function from sklearn model selection. Now one important thing that we had discussed last time is that uh, so the way so the problem doing test split, what you might find that you might segregate the data maybe in 80-20 ratio, that is 80% training and 20% data, but what will happen is the number of y's in training, y equal to 0, that is the 0th class, might be more in training and very less in the testing. So what will happen because of that is the model will train more on the data with 0th class rather than 1 class, and but in the testing you have more of the class 1 data. So what will it might do a lot of false positive, a lot of incorrect prediction with respect to that. So we want to avoid that aspect. So to do that, what we do is we we use a stratify, a parameter called stratify in test train split, where you are saying that for a y class of for a y class variable, that is a target variable, the ratio in which you're dividing a training and the ratio of 0 and 1 class instances in the training set will be same in the testing set as well. So assuming that if we have divided the 0 and 1 maybe in the 50-60 ratio kind of 50-50 or 60-40 kind of ratios, the number of samples present in training should be in the same ratio, should be available in the testing. So that's the one major thing. Another important thing doing training and testing that we discuss about, that okay, we have written the code, I have written the code, and you're going to return again, but there's a high chance that the testing train and the test splitting will be different. So how to make it reproducible? So whatever the accuracy I'm going to get and whatever the evaluation method I'm going to get, it should be reproducible to you also. So at that point of time, we give a random state as a parameter with any value. So in this case 40 I chosen, so you have to also put 40 in this case if you want to replicate the same thing, and you will observe that whatever the output I am getting within this notebook, you will also get the same. Okay, so that is two aspects we talk about test and train. Now with this some third section we talk about bandization of input. So for it is specifically MP neuron that it deals with 0 and 1 class. It contains only Boolean value, that is 0 or 1. But if you have seen the data, it is basically a real number, right? So if you can see my pointer, I am highlighting it. So all are real data, but NP neuron can consider only 0 and 1 value. So we have to convert that to 0 and 1. So how we can do that? So we can do something called bandization as of now, as a simple thing. So what we are doing, this is a plot that we have crossed. So we can assume right now that anything above 1000 can be considered as one class, and anything above 0 can be considered as 0. Anything below 1000 will be considered as 0. Anything above 1000 value considered as 1. Just for simplicity, if we such that we can tell that that okay, whatever the for 30 features we have, all the data will be transformed into 0 and 1. So once we are doing this, we get the data something like this, where the most of the data points lying either 0 or 1. There's no in between data. That's the binarization we are doing. Now while doing this, we get another important insight that maybe while training modeling the data, how you are how for each feature. Now here we are told that okay, anything below 1000 will be considered as 0 value, right? Anything about 1000 as 1. But what we have found that most of the parameters, if you can see in this graph, are actually is between 0 to 50 or 0 to 100 kind of like that. So this is not an ideal condition to say that all this will all anything below 1000 considered 0. So for each and every feature we have to see the range where we can say that anything. So let's suppose there's something called as radius error, okay, or let's say mean radius. That's the first thing. So what it so it has between value between 0 to 100 assume. So we will have to decide certain threshold where we can say that with maybe below 50 you can consider 0, and below 100 above 50 you can consider as 1, something like that. So to do for each and every feature we have used a function called pd.cut. Okay, so even if you don't know right now, that's totally fine, but you get what I want to tell you as a overall thing, that for an NP neuron you want a 0 1, you want to make a data into 0 and 1 class. Okay, you can't have a real number, so to do that you have to do binarize this thing. Okay, now once that is done, what we can do is we can try to infer it. Maybe we try to, since a very simple model, we can try to directly put an inference. So that means since in NP neuron we just need a parameter b as a threshold. Only threshold is a basic parameter here, nothing else. So we can just randomly put, in this case b equal to 3 we have kept. Let me increase the font. Okay, yeah. Okay, yes, that will be fine. So if we do b equal to 3 as a random threshold value, then we can just find out what is the NP inference, NP neuron inference, that is the model we are building, and how at the ground truth is, right. Now we are saying, but if you have seen from a theory lecture, randomly selection threshold is not useful. We need to find actual better threshold value which can work for majority of the points. To do that in NP neuron, we can only do is brute force thing, that is for each and every threshold we need to find what is the accuracy. So we have write the code, and we have found that so the what is the threshold value should be, it will be equivalent to either 0, the threshold value will be 0, or it is equivalent to the number of features present in the data set, right, because MP neuron is simple neuron, right, you can't have threshold. So in this case, the number of features are 30, so you can't have b equal to 35 as a threshold because you don't have that much features. So you have to find some you have to see that link between the number of features and the b value, right. So it is we're going to between 0 and 30 in this data set, right. So once we did, what we have found, for each threshold we find the accuracy of the model, MP neuron model, and we found that maybe for threshold b equal to 27 we found the highest accuracy as of now for 0.855. Now once you get this, now what you can do is inference, basically evaluation. How do you evaluate that whether the model is good or not, because the value that you are getting here is basically on a training data, that is a training accuracy. Okay, there's difference between training and testing accuracy. Training accuracy is something you do on training data, and testing is something, testing accuracy, which we usually talk about in general terms. If we tell that okay, this is our model is this much accurate, we actually tell in terms of testing accuracy. So that is something we need to work. We have to see. So when we did that for on testing data, we found that our value is basically 0.8. 0.778, or you say 0.8 in general, if you can want to summarize like that. Now this is something we have discussed, and the last thing we have discussed is a kind of template which we are going to use in the upcoming sessions, or in the Perceptron also, how a typical deep learning model can be written as. Okay, so let me again summarize this as well. So for any class of NP neuron in this case, a class can be anything. A class can be NP neuron, perceptron, a backpropagation, or a recurrent neural network, or any such thing. So but they follow certain template, and we are going to deal within that certain template only. Only the content within the template will change little bit here and there. So what are those template? Basically functions. So we will always, for a class, we will have a initialization function where we are going to initialize our parameters. In NP neuron we have only have one parameter b. In perceptron we have w and b. W is weights, right. Then we have something called as model, that is def model. Model is basically is a mathematical function. In this in the case of MP neuron, it's basically addition of the input value, right. And we have to see that whether the addition of the input values are less than, greater than threshold or not. And then there's another function called predict, where we're trying to see that how the values of x has been predicted by the model based on the threshold that we have decided. right? But the main function of all the stuff is fit function. Now what fit function actually tells about is basically a learning algorithm that you're going to write upon. So this fit function will tell about that. Now so in this case it's basically takes the whatever the learning algorithm is there, that is summing of the inputs, and come and change the threshold value based on the accuracy that you are getting, right? Okay, another important thing that you have to keep remember, that your accuracy will improve based on the how your loss function is performing. Okay, so if the loss function values are decreasing and accuracy increasing, that's a good way of looking at it. But if your loss function is increasing, accuracy decreasing, that's not a good way to look at, right? That means they have to tweak your algorithm something in such a way. Now once we did this, we have try and train and test this thing, and we got certain values. Till this point, we have discussed or we have coded in the last class, okay, in the last session. Now we are going to do for perceptron, and here I am assuming that you might know what's a perceptron algorithm, class algorithm will look like, but let's have a small surface of summary of what it actually do. Okay, now a perceptron algorithm will have one different thing apart from the MP neuron, that is for each input you will have weight. Weight will tell the importance of that feature while learning the algorithm, right? So if you are going to watch a movie, you're going to tell that okay, maybe the genre of the movie, the director of the movie, the actors of the movie are important for watching a movie, right? So what is the weight of genre, what is the weight of the actor? Maybe for actor you will have put more weight than the genre, right? Maybe for director you can make less weight than the actors. So that is weights that we are going to learn. So this is W in with respect to that, and there's something called P and N. P means labels that I'm going to watch a movie, that is the yes part, and the no, N with negative inputs, that is anything below the threshold, or in this case I'm not going to watch the movie, right? So what it is actually doing in a perceptron algorithm is it is checking each and every data point, okay, and what it does is it will check if it is belong to positive class, that is the value of output should be 1 in the instances. But what it found that the function model, mathematical model here is wi into xi, that means the dot product of weight vectors and the input vector. Okay, so in an input vector will have multiple values, like we have said the multiple features we have. For one instance you can have 3 or 4 features, 5 features, 100 features, millions of features, like that. For each feature you will have assigned one weight, so you're computing that as a dot vector. Now what you've seen that if the random input x is should be belong to positive class, but its actual value is when computing using mathematical model of dot product of weight and weight vector and the input vector is less than 0, you're going to update the weight. Okay, and if then it is negative, the point belongs to negative, but its dot product of weight vector and the input vector is greater than 0, then you're going to reduce the weights, right? And I hope the intuition you got that why we are updating w, why adding w equal to w x for updating for the positive points and w equal to w minus x into negative point. If you're not able to understand, please let me know in the chat. Once ended, maybe I can tell you a simple intuition about why it is happen, and it all belongs to the angles between the weight vector and the input vector. As a mathematical intuition we can talk about that later. Okay, now what we are doing is the template is same as MP neuron and is going to be same for others as well. That means we have certain functions in a class. We have functions like init function, a model function, a predict function, and fit function. Model function is actually the mathematical model through which you can define a perceptron basically, or any other model like backpropagation or RNN or CNN. Predict is function will tell about, okay, once my model is ready, I need to predict that whether my model is giving me good what kind of value is giving for each x. Okay, so that is the y prediction I'm going for each training data one. Now what fit function do? A fit function is basically a learning algorithm. That the one that we have seen just above is the fit function will do the learning algorithm. And you might have seen already in the, if you already used deep learning coding done earlier, you might have used fit function a lot. So the fit function actually takes all the input and the parameters. Parameters in this case are weight vector and the threshold, that is b. Once we take this, and it will iterate on x value on the input, and to get a proper values of weight vector and the b, such that it can fit the data. Okay, now this is the code that we have written, so I am not actually explaining here because it is same exactly like what is written here. So just a just a same way, that is self w equal to self w dot x. Self means it's just like the, in the class we have already initialized a variable called w. So this w is a class variable, not a function variable related to fit. So that's what it tells about, and whenever we have to update, we are updating the w and we are updating the b value, similar for such cases. Now we are calling this function called Perceptron. We are making a first object of this class and naming them Perceptron, and we are preparing the x train and x test, where we are going to train the data. Now we will provide x train and y train as an input and into a fit function, and it will train the learning algorithm. It will learn and it will find out. So whenever we saying learning algorithm, it basically learning algorithm find the parameters w and b in the case of Perceptron, or any other case it will just find the approximate good value of parameters which are going to used in that mathematical model. Okay, and then we plot the w. Okay, so what is so let me again maybe little reduce this. Okay, now what is, now here, from here the actual thing will start to for you to understand certain aspects. Okay, so what we are going to see here is how the perceptron. So here what we have done is we are plotting the value of weight parameter over the time for each vector. Okay, so what, since the weight of w and b will be iterated 30 times. Why? Because we have 30 features. So since we are using for 30 features, we are going to iterate 30 times to see that what is the amount of time. Sorry, 30 features, I will have a vector. Okay, so maybe the vector will be look like this. For each feature I will have one weight, so maybe let's say 0.1 for first feature, 0 0.0 0.002 for second feature, 0.0018 as third feature, likewise. Okay, now this is the for 30 features, whatever the weight we have given, it is getting like this. That is something you can visualize for each feature, what is the weight the model is giving. Okay, and you can do the training and testing and you get certain value with respect to that. And you can here observe that NP neuron, earlier in NP neuron we had the accuracy of 0.85, but now it has risen to 0.90. Okay, but now the question is, I'm not satisfied with this 0.90. I want that the accuracy should be increased more. So what I can do here, the concept of hyperparameter comes into picture. So what is hyperparameter? Hyperparameter is something which is outside the model, which will improve the accuracy of the model. Parameters like in person like WB, you can adjust the value to a certain extent, but to improve the parameter learning more and more, you can use something called hyperparameter. So we are going to discuss three major important parameters today. Okay. Okay, maybe I will take the questions maybe at the end, once this hyperparameters are ended, then I will come back to that. Okay, so first parameter is epoch. So in this, epoch means, so while I am learning the data of the breast cancer, that is I have 569 instances of that. So maybe the training actually was for training data set includes 512 instances. That means I have 512 rows. Now I am looking at those data point one by one at a time by learning using when I am calling this fit function. Okay, for each instance of row I am looking the one by one each instance and I am adjusting the weight vectors with respect to that. Okay, but I am still, what according to this code, what I have written here, it is going to run only once for each instance. That means once the 512 instances are over, it will going to stop. But what if I am again going to see the data again, might be my W and B parameters might improve, because by the time I am going to the last instance of the data set, my value of w and b might be has changed, but this changed w and b parameter values has not been seen by the first instance of the data set during the training. So again I have to see, I have to again go back and I have to see that how it is actually, whether the change value of w and b is actually making such the first instance or not. So that for that we are using the term epoch, where you will tell that how many number of times you want to iterate through that data again and again and again to improve the values of w and b such that your accuracy will improve. Okay, so what basically in simple terms what you're going to do is, this is the, I'm going to highlight, this is the basically your learning algorithm that you're going to write. Only the thing you are going to do again and again is you will iterate to each and point multiple times using the epoch. So that means you are adding an extra for outer for loop, where that once you get the data, so again you're going to run it, you again went to the data multiple times to adjust the value of w and x, and you will find the accuracy. How we do that and what is the how it will look like, let's see. So we have initialized the perceptron variable, and what we are saying, apart from giving for two fit function as x train and y train, which is the input and output, what will say that the number of times I want the function to iterate to the whole data set, how many times I want to iterate to that data set. So I'm going to present that. So let's say I'm going to iterate 2 times. Okay, now remember that our accuracy for one time is 90% for the training part. So let's see if I iterate the data 2 times, how it will look like. So it is running, and let's see. Okay, so I am getting some value of 90.08. Earlier it was 90. Yeah, 90.2, or you can say 0.902. Here it's for 908. So we have improved our accuracy to a good extent. Now let's see if I do for 10 epochs. That means I'm going to iterate through the whole data, training data 10 times. So how it will change. Okay, now what the figure here you can see is, I'm going to tell before, but you can see that our accuracy has been improved a little bit more. From 90.8 it is come down to 91.6. Okay, so I'm just multiplying this value into 100, based on that I'm telling you. And the what it is telling is, this graph telling that for each epoch what is my parameter, what is my accuracy over all the epochs. So it is telling me that what is the maximum accuracy I achieve for each epoch, it is telling me. So let's say I'm going to iterate for maybe 50 times. Still much better improvement, that is from 91.2 to 91.9. So you can see that as I'm increasing the epoch, my accuracy has been improving. So maybe let's say 100 this time. Now it is from 91.9 to it became to 92.18. Obviously it's a gradual improvement, but you can see that this even gradual improvement is important for us while training the data. So just by one hyperparameter that we're talking about, that is by just by epoch, we can improve the accuracy, at least in the case of perceptron right now. In generalization, we have to be very careful about how many epochs do we want, because here the data set is only consist of few KBs, that is like 576 data points, 500 or 600 data points. That's why we can iterate 100 times and we can get it fast. But let's suppose you have 1 billion or 1 billion data points where you have to train the data and you don't have that much compute resource. So the number of epochs might not be might become counterintuitive, because here for running 100 times I'm getting the results maybe in 3 or 4 seconds. But for the big data, the bigger data is, the more time it take to train to learn the parameters. The more time it take, even for one run, that is just to go from 1 billion parameter, 1 billion instances are there, it might take maybe a half an hour, an hour. Let's assume that you have a good system with respect to that. But if you're going to run that 100 times, maybe it will take months just to train that data, and the accuracy will be again like minute difference that like you see, like from 91.9 to 92.1, that will be this, but you are taking the whole month time just to improve that accuracy. So that always epoch is not a good way, but just to get an understanding that the more epochs you do, the more better the machine can understand the data. But you have to have a trade-off that how much time it is taking to train one epoch. So if it is taking less time, then obviously you can take you can increase the epochs. Okay, so I hope you get this point of epoch in this case. Now if you do this, since the training accuracy is improving, obviously your testing accuracy will also improve because it is looking at more and more data. So that's a kind of proportional aspect to that. Now another important point in this thing is checkpointing. Okay, so let's see what checkpointing is like. So it's not actually a hyperparameter, but it's a usually a practice where what you're doing is now you're running this model to 100 times, right? 100 times it you're making it run to the data again and again and again. But if you can see my cursor here, you can see that there's some small bumps are there, that is below is there something, it is increasing again, something decreasing again, increasing again, decreasing, like that, right? And by the time you reach 100 epoch, you'll find that the value here at 100 epoch might be less than some of the epoch where you get the maximum output, maybe in this case 92.1. so I'm just presenting here the maximum accuracy I'm getting, not the accuracy of the model at the 100th epoch. So that is something I need to make sure of that. So what you can do, checkpointing, what you do is you can run the model 100 times, but I will keep on saving only that model which has giving me the best accuracy. So checkpointing is doing for that. So what it will do is it will save. So if the moment I got the maximum accuracy till that point, I will save that accuracy and I will save the weights, I will save the parameter values also, that is the W and B. Like that I will save those values, I'll keep it stored. So the moment again in some other epoch I will find that okay, now my weight vectors and the threshold value has improved, it is giving much better accuracy, I will just change that checkpoint like that. Now why it is important here, you might be using W and B as two parameters, right? It might not be big, but when you actually started creating deep learning models, complex deep learning models, the weights will be in the terms of thousands or millions or lakhs, kind of like that. So you have to keep on checking that, you have to keep on storing the weight, otherwise all the weights that has been learned hardly by a lot of time, taking a lot of time by a machine, it will lost, all these things will lost. So you have to keep checkpointing as this thing to store the best values that you get for your parameters. So this is not a hyperparameter, but this is something a best practice that people use, and we're going to see that a lot with respect to that. Okay, now another important thing I'm going to show here is, okay, so earlier till this point we were looking at the value, it is the value of accuracy with respect to this, right? For all the epochs we are getting the value between 0 to 1, kind of like that. It is another way. Now once we do the checkpointing aspect as well, it's not that different from the one that we are seeing here. Only the scale has been changed, that is instead of 0 to 1 we are just keeping the scale between maybe 0.8 to 0.92, because that's the max we are getting. And if we, because we are enlarging that, maybe we are doing more zooming into that, and we can see that when we deal with zoom in the values and all, we can see that there's a lot of bumps are there, there's a lot of below up, like that. And ideally actually we don't want that. What we want is suppose I reach to a point of, let's say if you can see my cursor in this point as point near 0.91, I want that the next epoch should be within the range of 0.9091. It should not go down to 0.86. Okay, so my gradual improvement of the learning should happen gradually, not drastically. So I should not get this sudden bumps stating like that, because it will confuse me, it is very random. And that is what we are going to learn in sigmoid neuron, that how the graded descent aspect come into picture in this case. Okay, and how the learning parameter, which is the next parameter we are going to discuss now as a hyperparameter, will improve this. So again what we want is, so when we are plotting the accuracy, we can see that after reaching 9.1 0.91, I'm directly getting down to 0.86 or below, like that. I don't want that. What I want is that after 0.91 I should go to 0.92, not to 0.86. maybe I can go little bit errors like 0.9, 0.9, but not below than that. So to do this, we can put learning rate. That means when we are learning, here this is a code we are putting. So what we are doing, learning rate. So when we are upgrading the values of our w and b, we should do it very small, small. We should take very small step towards that. That's why you might have heard that learning rate usually we deals with 0.1 or 0.001 like that. So importance of learning rate is that when you're updating your parameters after certain computation, you should update the parameters in such a way that the increment of the accuracy should be very less, small. It should gradually go up like that. And I will just show you the demonstration of that as well. So let's say, so here the same code is there. Only what we are doing is, instead of w equal to w dot x, let me write. So this is what our updating parameter looks like, right? So here what I am doing, instead of because here we are adding x, right? So here instead of adding x, we are just putting learning rate also. So here learning rate will be in the range of 0 0.1, 0 0.01, 0 0.001 like that. Okay, so where whatever the value of x will be, maybe 10, it will reduce down to maybe 0. If you multiply with 0.1, it will come down to 1 kind of like that. Okay, so we are slowly increasing or decreasing the weight of the decreasing or updating the weight parameters with respect to that. So let's see how it will look like. So when we are in the fit function, apart from epochs, that is this 10,000 is epoch. Let's start with 10 right now, and let's give up learning rate of 0.1 as of now. Okay, and let's try to run this code. Now what you can see here, you can't see the little bumping right of kind of like that, right? You can't see that bumping right here. You can see that this kind of straight line kind of this is there. Okay, and you're improving because of learning rate. Now for this case you're getting 91.6. Earlier, for if you're trying to run for 10 epochs, you're getting something 90.8 kind of thing. So it's learning rate also improving the accuracy with respect to that. So let's increase it by 100 let's run the do it epoch 100 times, and learning rate keep as 0.01. Okay, now see, we have our accuracy has been jumped to 92.38, which is pretty good with respect to it, right? And now you can see that even the learning that is happening, the updating of the weights and the accuracy, it's not changing drastically. It's happening very slowly. Even if you take a big enlarged view of this, you can find that it's still between 0.91 to 0.92 between to 0.9 or 89 like that. Okay, now let's now see that you know that already that because of epoch your accuracy has been improving, right? Let's, if we give more learning parameters, more less value, how it will going to run. Let's see like that. Now we have seen a little kind of jump here, which is some kind of analogy which should not happen here, but it's still, you can see that 92.38 is happening. Okay, learning rate, let's again try to see if it is going to affect anything. Okay, so again it is giving me very less improvement with respect to that, but if I increase the epoch in this case, it will take some time. Now from 92.38 to 92.96, right? If I reduce this learning rate and keep the epoch same, that is we got approx 93 accuracy, we still got the learning rate like this. So it's in this case you might not get the as apparent thing, but we can I can tell you for sure that the moment you change the parameters of learning rate and let's say 10,000 times and all, it will improve the accuracy very drastically, okay, for you. And obviously the updates of coming from 90 to 94 take a lot of time, talk a lot of epochs and all, epochs and learning rate, but I think you got the just that, just these are the reason why it called hyperparameters is because you are not changing anything within the model. You just, what you are changing is just that how many times you want to look the data again, how many times you want to train them, and to what extent you want to update the parameters like. Okay, so from earlier we have seen 92.9, we have jumped to 94.33. Okay, so So what we can say, that is the impact of epochs and learning rate, which you're going to use a lot in your deep learning content, like when you're going to make a develop a code and all that. Even going to we see that, see in back propagation and CNN and all those development, we will see that the moment we change these values, it is going to it is mostly we're changing this value to improve our accuracy of the model. Okay, because learning parameters will give you to a very good amount of accuracy, but after that maybe it is giving me accuracy till 80%. From 80 to 90%, if I want to you if I have to go, I have to use basically these hyperparameters of epochs and learning rate. Okay, so this is what we have discussed with respect to this is the code look like, and you can tweak it. I have just shared the link also in the chat, so if no one has it, please share it again. If you have question, let me see the chat basically here if someone has question. Okay, in code 50, what is on y-axis? On axis its fate is for 30 features. Code 50. Okay, let me go to there. Here I think you might be talking like this, right? Okay, so this 30 is basically number of features, and the y is actually the weights you are providing to each and every feature. So you might find that for number feature maybe 4, let's assume 4, you are giving weight of 3000, 4000, and maybe for feature number 23 you are giving near to 90 3800 minus 3800, like that. So the important thing, weight doesn't need to be within 0 and 1. You can normalize it obviously, but it can be within the range of any real number, so that is totally fine. Okay, so these are the weights of the uh, individual features that we are talking about. For if we do for, and if we write down all the feature name, I should have done that. If we do that, we can see that for which feature what is the value of weights that we are getting here. Okay, what does epoch mean? First epoch, so again epoch is basically, we are now, once you have done the training and testing data, now training data will have certain amount of points, and if you whatever the learning algorithm you're seeing in the theory course, it just mostly talks about the iteration of the learning algorithm from all the data point one time in the training set. So suppose I have 512 data points in the training set, the learning algorithm will traverse through those points only once. Okay, but what you want that, okay, now I have updated, again I have to go and revise to see that whatever the point parameters I am getting by the end of the last instance of the training data set, whether it's correct for the first data point also or not, because we haven't checked that. To do that, again it will go and check, and it may find that okay, some error is still present, and how you find the error, you find using the loss function basically. Now once you find that, you will again adjust the weights. So the adjustment epochs are basically to adjust the weights, such that whatever the adjusting of the weights are happening, you want to make sure that the final product is actually has been seen by all the instances, and so that you can accurately or at least approximately fit that data. Okay,
So can you move to code line 47?
47. Okay, this one. Oh, this is the actual code with respect to
Yes.
Perceptron. Yeah.
In the last section, you have added and subtracted 1.
Okay.
Added x and subtracted 1, and vice versa for y1 and y0.
Yes, yes, yes.
So please explain this.
Okay. Okay. So just to give a little bit more intuition with respect to this, uh, so what it is happening is, okay, give me a moment. I will share the screen of my iPad where I can write and I can tell you what's it look like. So I hope you can see this screen. I'm going to stop this, and I will tell you the intuition with respect to B B1 and this. So let me stop sharing this and share the screen. Okay, let me check whether I'm getting this or not. Yeah, I'm getting this. Okay, so I hope you can see the screen like this. So
Yes.
Okay. Now what actually happens is, now you have to, I'm trying to visualize it. Okay, so let's say this is the 2D graph, assume just for as of now, and you have a W vector, this is something called W vector. Okay, uh, and this is something called X vector here. Okay, uh, okay, let me do some other thing here instead of like that. Okay, so this is the case. So what does it means is, now I have a vector of x which is less, which is maybe less than 0, or like it should be belong to class 1. Okay, but its wi xi value is less than 0. That means I have to update the vector, right? So what I will do, I will do w equal to w plus x. So what is happening is, in this I will do a vector addition like this. Okay, I will add, and somewhere here my w new will come. Okay, now once you get this idea that how this w equal to wx is happening, because of this vector addition of this, I am getting w new, and which is closer to this. Now why it is important? The important is because of the angle, what we are doing, we are trying to improve the angle between x and w. So usually the angle between vectors we found out using cos theta. So this is usually a function like. So what we are saying this, if the value positive is on any cos theta value is between 0 to 1, right? Cos value can lie between this. So cos 90, this is there, this is cos 0, and this is cos 180. Now if you get this idea that anything between 0 to 90, my value should be positive, that is the value should be positive here. That's why I'm adding this value, says that the angle between x and w should be acute angle. Acute angle, you know, this between 0 and 90. And if you want to have it negative value, it should have, you have to decrease this value, you have to negate, you have to subtract this vector with this, such that you can get the value between 90 and 180. Now once you get this point, already understanding that okay, how cos is actually helping us to understand that how the weights are actually going towards the particular instance, now comes the b part. Now b is basically called as intercept. Okay, to again explain it this, so suppose I have a data here, and let's say something as green like this, I have red and green kind of thing. So I have to fit a line, basically perceptron like this. Okay, now this w slope, w will tell me the slope of the line, that is how it should look like. Either it should look like this, or it should look like this, or it should look like this, like that. But what b is telling me, where the intercept should be look like. Intercept will be there. Intercept means where, from where I should start my value of p. So let's say I'm doing like this. um, let's say I'm taking blue for better understanding. Let's assume that I'm selecting this blue line as my final thing. Now for this I need to get a b value, that is the intercept on the x-axis. Why x-axis? Because this is where I am trying to understand, from where I'm trying, my data point lies, and its relation will tell me its x relationship with respect to y. So when we are doing b equal to b minus 1 or b equal to b plus 1, what we're trying to do is we're trying to move it. Now what does it means? Here blue line, you can see that it is there something, let's say 50 in this case, but I want that my better fit line will be like this, the another blue line that I'm crossing right now. Here I say that if my intercept is 70, I can cover most of my data points which are actually present in B, and I can separate the red and green points. So what it doing is it is actually moving my points in the space. Okay, moving my slope in the space. If I am going B minus 1, maybe it is going backwards here in this side. If I am adding it, it moving this side. Okay, so b is basically intercept, and it is helping me to move my slope either to right side or to the left side. So that is what the intuition of b is here. Is that you getting little bit intuition with respect to that?
Yes, yes, clear.
Okay, so just basic to move this slope towards a particular direction, we are using b, and b is basically intercept here in this case. Okay. uh, okay, is there any other question? Okay, so fine. So that being said, it's almost 7 also. So maybe we can take a 5 minutes break, and then we will start with perceptron learning, and we will go but how we go to sigmoid, and why sigmoid is the building block, sigmoid neuron, and why it is a building block for deep learning networks. Okay, so we will talk about that. Okay, so we will talk about, maybe we will come back by 7 and we will talk about that. So this is a little, this next part will be a kind of theory, but this will be helpful because from next session, since we are again going to code the back propagation, I think that's the first topic we are going to talk about, and here we are going to also discuss the gradient descent aspect as well, which we have seen to a kind of extent right now in our code, but we will make it more explicit, the concept of gradient descent in the sigmoid neuron as well. Okay, so please come back by 7. Okay, I think Noel Maria has raised the hand. If you can ask the question if you have any. Give space with this. Okay, we will start with this thing. This is a more theoretical part, so please bear with me. I hope you will learn some exciting stuff with respect to this. Okay, so not this. Yeah. Okay, so before going to sigmoid and basically from perspective of from Perceptron, which is basically a basic learning, and to jumping to sigmoid neuron, and from which everything will be based upon, right? After the sigmoid neuron, you will learn that how to combine multiple sigmoid neuron. That is what will happen. And once you get this idea, then you will learn about backpropagation, how it is going to happen. Then you will go to the RNN, that's the recurrent neural network, and then with neural network, and then convolutional, and vice versa. So this is usually the flow is usually like, okay, till perceptron mostly the basic understanding is there, but game changes when the sigma neuron comes into picture, right? So we are before going to that, why sigma neuron comes to picture and why it is very very important for us to understand from a one simple perspective. Let's understand the limitation of perceptron. Okay, so if you can see on the screen, there's a small table is given, right? So in this, that can a person can buy a car given its salary in thousands. Okay, so that is given as 0. 1 means he can buy the car, and 0 means not buy, the car. Okay, so that usually means like that, and we can actually we can make a proper uh, we can make a, what you say, we can make plot in the graph, and we can get the graph like this. Now by visually and by if you run the perceptron algorithm, you can find that this will be a threshold where the green points that is on the right side will say this is the one. So you will find maybe, let's say, the 50. So any person who buy 50K uh, salary can buy a car. Anything below 50K cannot buy. Okay, uh, can buy a car, and here cannot buy. This is what data tells us. But if you actually observe, is what about if I have a person which has 49.5K or 50.1K? Doesn't mean it's a contract. I can say that 50.1K I have a data point which cannot buy, but 49.5K can buy, right? So these kind of scenarios are very common in real world data set, and these are quite kind of approximation, this kind of very real values, where what we are doing is we are putting a hard code. This is a very harsh threshold kind of thing. Okay, now why it is harsh threshold? Because it is coming from the concept of linearly separable. So if you have from theory, if you have heard the concept linearly separable data, that means a perceptron can learn the data only when the data points of class 0 and 1 can be separated by a line or a plane or any other dimension with respect to in a linearly equation, right? So it's a kind of harsh threshold. It is not equating. So it is telling that even suppose this, it might be maybe 49K, okay, and this may be like 11K, okay, it is giving same weightages to 11K person and the 49K person, even though it is just 1000 less than the threshold salary point that we are talking about, right? But ideally in this scenario, you should not consider, you should give some priority to this 49K, okay, and some priority to this 11K person. in this case. So this is what we're going to see, how sigmoid function we're going to resolve this aspect, at least from the perspective of loss function. Because even the loss function, if you can recall, it is like, if I remember correctly, it is like y is not equal to y hat is not equal to y. That means if uh, if y hat, which is the predicted output, is not equal is okay, if y hat is not equal to y, ideally it should give 0 value. Okay, and if it is equal to y, it should give me 1 value, something like it is like that. This is a loss function, typical loss function, that if y equal to y hat is equal to y, this is, I am getting the same output as ground truth, I am giving 1, otherwise I am giving 0. This is the loss function here. Okay, but the problem with that is it is keeping the 49k person and the 11k person into the same range with respect to that. It should give a certain weightage or certain priority to the 49k as well, maybe as a less loss value, loss function value in this, or maybe it should give us high loss function value. Okay, so this is something that is a one major parameter. Is not looking at the boundary conditions by a perceptron learning. It's not considered the boundary condition. That is the one thing. Why? Because it's because of the harsh threshold that we are getting uh, keeping as it is. That's the first thing. Second thing is the linear separable. That means the data set has to be linear separable. That otherwise, if I have a data point, maybe let's say here near the 40k, see the blue line, green point that I'm putting here. If I'm getting like this, it can't handle this kind of condition. It should have either I should have green points on the one side and the right and on the left side I should have a red point. It is thinking like that. So this is again making me a challenge that I should have a linear data with respect to it. But most of the data in the world are non-linear. That the relationship between them will be very non-linear. Okay, so these 2 points is basically is telling us the reality that even though perceptron can deal with real numbers, but the learning is still very inadequate, and we will try to see that how sigmoid neuron, to a certain extent, not to a very good extent, but to a certain extent, will drastically improve this learning. Okay, so this is what we're going to talk about. So before going to the sigmoid neuron, we have something called as 6 jars of machine learning, which we have talked in the first live session. Okay, so it has some real inputs. The first jar is data. So in data, perceptron can have real inputs. That's the first thing. Perceptron can only do as of now classification, that is Boolean input. It's not, the regression is not come to picture as of now. The model is basically the dot product of w and x, that is weight vectors and x, and should be greater than or less than or greater than equal to the b. That is one thing, and it should be have linear separable data. Oh, I should write here, it should have linearly separable data. Loss function is actually defined as sigma of I 1 if yi is not equal to y hat. It's like this, so I will need to check how this loss function is, but you can understand this loss function. And perceptron learning is the learning algorithm that we are talking about, that we had seen just now, maybe a few minutes ago. Learning algorithms, how it updates the weights, and evaluation is basically accuracy. Okay, any good deep learning algorithm they are going to learn right now can be classified within this jar. This is the recipe, and you should be prepared to look the jars into this aspects only. Okay, you don't need to go anything about like that. And what the major thing you're going to learn in any kind of technique you're going to use is the learning part. This part is easy to understand, this part will be easy, this part will be easy to a certain extent. These are very standardized. These loss evaluation tasks are very standardized. Data will be different, model may be different to a certain extent, because the what we say, the kind of mathematical intuition will become complex. But the learning algorithm is the most complex part, that we should know that it tells about how to learn a parameter, how to learn a parameters or parameters of the model. Model, we are talking about this function. Okay, so this is model, this is learning. These two jars are different. Okay, so this is what generally we talk about. Now what we are going to look ahead right now is with respect to the sigmoid neuron, so what it can do. Okay, so let's quickly recap, summarize what it can do. It can take, apart from 0 1, it can take real inputs, which perceptron can also do. It can do regression. Regression means uh, it can deal and give output in real numbers, not as 0 1. Perceptron can only give 0 1 as output, but because of regression, it can give real number as output, but to a certain constraint. We will talk about that. Now we talk about harsh boundaries or harsh threshold that we can talk about, right? It try to resolve that aspect also. So instead of having just one straight line, it would try to have a non-linear relationship where it can try to give me a kind of line like this or line kind like this, the kind of boundaries that we're creating. So it can become non-linear, but in this case sigma neuron, it will be kind of S. So we will look at the sigmoid family of function. So it deals with the sigmoid family of function. We will talk about that. Okay, so it can deal with the smooth at boundary. That means it will not strict one line, but it can be a kind of curve or non-linear relationship will be there. I'm sorry for this, but it is wrong. I'm not able to take proper screenshot, but it is like, is a basically mean square error. That is mean square error. So what basically you are doing is you are trying to whatever the predict, this is a predicted output, this is a ground truth, this is a ground truth, and just you're you're taking a difference and just squaring it. So this is a mean square error. Learning is more like a more generic algorithm. Okay, this generic algorithm is basically deals with the gradient descent. Okay, that we are going to discuss that part. And accuracy, apart from accuracy, this is accuracy is for classification. So wherever accuracy comes, you just assume that this is a classification. And for regression, it is something called as RMSE, that is root mean square error. So we're going to test that part as well. Okay, so these parts are going to change. So what are going to change? Task is going to change. Input is same as perceptron. It can take the same input as perceptron as well. Boundaries, that the boundaries that we are creating, the slopes, the line that we are going to deal with will be smooth. That we can have curves with respect to that within the context of sigmoid family. What is sigmoid family? We will discuss that. Now, instead of having the loss function like earlier, we will deal with mean square error, which is standardized one. There's something called as cost entropy. I think you might have heard already if you have read the back propagation stuff also. We will discuss maybe later in the next session. Okay, algorithm is more generic because you bring the concept of gradient descent. It will be more intuitive, and it's more principled way rather than random guessing that we are deal with the NP neuron part. Okay, rather than a brute force. And for accuracy as evaluation, we'll have a classification, and for regression, it is for root RMSE, that is root mean square error. Okay, now how sigmoid function will look like in a general sense. So that function will actually is y equal to 1 plus 1 divided by 1 plus e raised to minus power wx plus b. Now two things here. Here x, we are assuming there's only one feature. Okay, right now in this. Okay, and there's b. So here parameters are also same. There's a parameter of w which is same as weights, and there's a threshold. We talk about, but in this case there's no threshold. It is, now we will talk w as a slope and b as an intercept. So how to take intuitive, before that, before looking at this graph, 3D graph, let's talk about something else as well. So this is for 1. Now if you want to have two inputs, less two input features are there, we just add that e raised to w1 x1 w2 x2 plus b. Okay, similarly for 3 it will now this will give this kind of graph. And if you want to have more number of input, then you can write sigma 1 equal to 1 I equal to 1 to n wi xi plus b. Now you know already this wi xi is basically w and x are vectors, so it's basically a dot product. So what we can write this as I 1 e raised to w transform x, that's a dot product, plus b. This is the final, this is the function we are talking about. Now this function you can also tell as a sigmoid function. This is a sigmoid function, or you can use a logarithmic function, class of functions. So lot of functions are class will be come to this. Why? Because sigmoid function will deal in the terms of s. So maybe this might be a sigmoid curve, okay, might be this can be a sigmoid curve, okay, uh, this can be a sigmoid curve. We will if you want to show more different type of sigmoid curves, let me show it. This is multiple kind of sigmoid curves are there, where does this, if you can see that this is a slope kind of thing, okay. Now intercept, what we talk about intercept here is we talk about when x is equal to 0, okay. We want the value, the slope intercept here b value will come when my accuracy is 0.0.5 of a particular model, and here it, in this case it might be 0, but in this case 0.5 is maybe in the -1, so b will be in -1, okay. So why it is there, we will mathematically intuitively tell you that, but again you can see that slope will gives you w, and how to move it, if you're moving right side or left side, based on that the value of b will change. So this is the intercept. The intercept will come in this case when the value of b is value of equation that we have seen, that is 1 plus e raised to wt plus b. This equation we are saying that when the value is 0.5. Why 0.5? Let's go back again and check it. So why 0.5 is, suppose my w is 0 in this case, okay, let me write it again. Okay, plus b. If I have this, okay, if I keep w equal to 0 and b equal to 0, if I put this into this value, it will become 1 plus e raised to 0. Anything raised to 0 will become 1. So it will become 1 plus 1 by 1, it is equal to 1 by 2. So that's why it is a kind of standardized point, that because most of the when we are trying to learn something, we'll start with something, either value parameters value as zeros or ones, mostly like as a random number, right, to initialize the randomness like that. That's why if we keep 0, mostly 0 is a standardized process. That's because of this we get this function value, that is the fx in this case, as 0.5. That's why we keep 0.5 as a important. Whenever you see 0.5 as a function equal to fx, directly assume for this sigmoid neuron that w equal to 0 and b equal to 0. Okay, this is a standardized process. Now coming back to the this function. Now this function, if you can see, it's a basically 3D function. This is for two inputs that we are having, that is x1, x2, okay, and this is the fx value that you are getting, okay. Now you can appreciate from this graph why you can deal with regression here. That means here fx, that is y cap, you can, your output will be between 0 to 1, okay. It's not like directly here this part and this part, it's not like this. It is there's a proper in between kind of proportion is also there, right. Now once you understand that there's a kind of S curve will come with the sigmoid function, sigmoid neuron, now I want you to visualize certain aspect with this. If you can observe, these are multiple colors are here. So if you can see, this part is red, this part is green, maybe this part is yellow, kind of like that, right. Now if you can see, if you can see from top, obviously it's a little hard to understand this kind of points, right. But if you can look from top, what it will look like is like this. So you will look at that, okay, from a 0 to 0.1 kind of thing, uh, the green part in this case is closer to 1 and the red part is closer to 0, like that. Now, why this is important for us to understand here? Now, for now this plot has been done for the two input case, that if I have a salary and I have a family size, these are my x1 and x2, and I need to tell whether I can buy a car or not. Okay, I'm going applying a sigmoid neuron, that model of the sigmoid model function, mathematical function I'm going to apply like here. If I do this, now you can see that the threshold that you're going to make is will be little different. What that means is, you can see that the points here, the red points, the red color point, if you can see, here the some points are there. Maybe I can use black here. Yeah, this some kind of points are available here. So the model short knows that this points belong to the red class. Similarly, this green class, they should know for sure that it's belong to the class 0, that is class 1 kind of thing. But the middle, the thing that is the orange yellow part kind of thing, the light green part, here they're giving an estimate with respect to it. So yellow part will just like a 50-50%. This is like a 50% that the model either can belong to the 0th class or the first class, like that. Okay, but it is giving us a weightage also, that maybe in the 50% kind of thing, some points, there are some green or red points are available. Okay, so it's kind of giving a probability. Probability means 0 to 1. My values are between 0 to 1, and it can be 0.49 or 0.51. Because of this, I can, at least via regression, I can tell that, okay, I have, if I want, given I have a maybe like 4 lakh in LPA and I have a family size of 8, I'm getting probability of, maybe I will give a probability of 0.9. So I may say that, or maybe 0.21. So I will say that, okay, my probability of buying car will be less, maybe d 0. So it is still fine. Okay, but if I have a family of, I have a salary of 11 lakhs and 5 family size, and I'm getting a probability of 0.51, I may think that, okay, it might be closer to the positive class rather than the negative class. So it is giving me some approximation with respect to it, and that approximation is good for me. Why? Because it will help me to understand the calculation of the loss function. Okay, it's not directly that I will say, okay, no, this is 0 class and this is 1 class. This is not I'm doing here. I'm just stating that this regression is there. Obviously, if you want to make it as a classification problem, you can say that, okay, like this like this S curve that we have seen from this curve, we will say anything above this is class 1 and anything below this is class 0. Obviously, we can do that because we just need to put threshold, right? But we not interested in threshold aspect as of now. We are interested is, given the parameters, input features, how close it is actually to class 1 and how close it is actually to class 0, and what is the probability with respect to that. So, and why? Because sigmoid function will always give me value within the range of 0 and 1 only, because of the equation that we are having it. So if w and w equal to 0 and b equal to 0 is there, you know that I will get fx value as 1 by 2. Okay, because it will become like 1 equal to 1 plus 1. But if I want to go to closer to 1, that if I want fx is equal to 1, then what I should do is, I need to decrease this value. So maybe I will say that maybe e raised to minus 8000 kind of like that, or maybe let's say 300. Okay, so it will become like 1 plus 0.0000000 something like this will be there. Okay, with the exponential value of such that, which is very insignificant. So even, and if I divide anything by like if I have 0.0008 kind of thing, it will give me some value of 99.99999. It is still closer to 1. It will not reach 1, but it will still closer to 1. That is what is important to us. Similarly, if I want to go to class 0, that is fx equal to 0, I need to increase the value. So maybe 3 equal to 300. So maybe I will find that 1 equal to 8000. I'm assuming certain value. I don't know exact value of exponential raised to 300, but let's assume it's 8000 right now. So it will be like 8001. So obviously it will be some, this 8001 value will be closer to maybe 0.000067 kind of like that, which is equivalent to 0 kind of thing, right? So if the value of e here is positive, my function will go towards 0, and my, if my function e is to the power of exponential is negative, it will go closer to 1. So this is something you need to understand uh, as a mathematical intuition, like, okay. So at now that has been said, now you can see that if you want to visualize a 3D thing, if you put it on 2D, it will look like this. And what sigmoid function is doing is just giving an approximation of probability that, okay, given a particular instance of the data set, my data will be closer to a particular type of class, either 0 or 1, but it is not saying exactly, okay. It is on us whether to put threshold or not, but in our case we don't need as of now. Okay, now this is there. Let's see what else. Okay, so the next question is, how does a sigmoid function change when we keep w and b? Now you have already seen that from the mathematical in this mathematical model itself, that if what is the equation, this wx plus b, for this equation, if I get a positive value as final output, my value will be closer to 0. And if I, for wx plus b, if I'm getting as negative value, it is getting closer to 1, right? The whole equation of fx, it is closer to 1, right? Now but we want to know that how the importance of w and x will going to affect us, okay. So what, how we can see is, so let's assume this is the, some data point is there, and this is the kind of slope. Now again, the when you talk about slope of a line, you have to see it's a positive slope and negative slope, okay. So positive slope means, let me give you a little kind of refresher here. No, okay. So if I having a line like this, it is means it's a negative slope. Why? Because this is x, this is y, and this is x. So as my y is as my x is increasing, my y is decreasing. Oh, and as my y is increasing, x is value of x is decreasing. So this is a negative slope we talk about, right? And this is a positive slope. That means as my x increase, y increase. So it's a proportional to it. So when we say this, this is a, when we talk about slope of a line, we talk about in which direction it is going to, and w is basically helping towards that. So if the value of w is positive, okay, it is it gives us a positive slope in this kind of scenario, okay. If the value of w is negative, okay, then, and when we are saying what is a negative, since w is a vector, we are talking about the w, the norm of the vector, okay. That is scalar value which define the vector value, because vector is both direction and the quantity. So we are talking with respect to the quantity here. So but if the line is like this, here the slope will be negative. So here the value will be negative. Now this is with respect to w, that you know. Now as earlier we also discussed here, that what is the relation of b aspect here. So what b is the doing is, as we are, if we b will help to shift the slope. So b helping to shift slope in either right or left direction, okay. So while learning the parameters, it will ask the slope to go here, or it will ask the slope to go here, okay. So b is basically like that, and b is intercept here. So we already covered this part few minutes ago, like in the first phase of the this session. But again, you get the intuition, like how you're doing it mathematically, we can derive this, but as of now, if you just get this intuition, that is totally fine, because then you need to understand that if you want to know mathematically also, there's a concept of that how there's a, to define the value of b with respect to a relationship of x, you can see, the equation will be presented like this, okay. So how it will do that, we have to it derives from the line equation. So let's not get into this aspect, but you can understand that w is for slope and b for intercept, but it tells about to how to shift the slope, in which direction I need to shift the slope. So that is what we are going to talk about, okay. Now let's talk about something called as loss function. Loss function is uh, y hat minus y square. Okay, this is typically a loss function of a sigmoid neuron. Okay, now let's assume that y is actually okay, let's see here only. It's a relationship. Now we have some points x1 x2, and with this is some y values there, and it's predicted, this is a predicted value. Okay, and look at the relationship with loss function. Now if you can see, the difference between 0.5 and 0.6 is 0.1. Okay, let's write it here, 0.1. Okay, here also 0.1 is 0, and this is 0.4. Now if you want to relate this with respect to square, if you square them, the effect of these three will not be that much, these 3 points, first 3 points. But if you can look at this, if you do the square, the effect of this will be way more, because 0.1 square is basically 0.01, but for 0.4 square it is giving me 0.16, which is way greater than 0.01. So what you can understand intuitively from this loss function is that the more the difference between my actual and predicted value, the loss function will take care of that, and it will give me a higher loss value for this. But if my loss function is nearer, say if the difference between the actual and predicted is very less, the loss function will give me very less value with respect to it. So it's a kind of weight, you can consider it as a kind of weight of the preference it is giving to the particular point. Okay, coming back to let's say here, the point of green here, if you can see, oh okay, let it change the screen first. Yeah, if you can see the circle and black highlighting, so it's actually nearer to 1. So even though it has some kind of some loss function will be there, some differences will be there, the difference will be very less compared to the green point which is present here. Again, I'm circling multiple times, right? So it is adjusting with respect to that. Otherwise in perceptron it will give the loss either as 0 or 1, but it is not giving the priority that which function is actually, which point is actually contributing to the more loss. And why it is important? Now since I know that this fourth point is giving me the higher loss, my learning algorithm will try to adjust this point. Learning algorithm will try to adjust this point. Basically it will try to say how I can minimize this loss function. So that's the beauty of the sigmoid function that we are talking about, and how it is related to the loss function here. Learning algorithm will take the input from here, and it will say that okay, these are some of the points which are giving me very high loss, so let me focus on that loss, and let me focus on that point, and let me try to see how I can minimize the loss, or I can improve the accuracy of by fitting the line onto those points. So that is what it is trying to tell us. Okay, so that being said, let's talk about the learning aspect. So this is the fifth jar which talk about, this is a learning algorithm. Okay, now it depends on you. We will go to mathematical aspect. Otherwise, we'll try to give a simple basic intuition with respect to the sigmoid neuron. Okay, so this is kind of in simple recipe of telling a learning algorithm. It I think you have already seen that in the lectures. So there is something called as initialize, iterate over data, and tell satisfy. So this is the kind of template for any learning algorithm. Okay, initialize will be the parameters. Initialize will be the parameters based on the from where the parameters are coming from, the model, the mathematical function which defines the sigmoid or perceptron or any other DNN model. Okay, so we initialize the parameter, in this case W and B. Okay, now we will iterate over data. So while iterating over the data, what we try to see, we try to adjust the weights of W and B. So we might say W plus delta W and B plus delta B. Generally we do this kind of step, right? This is again a kind of template we are doing, and we are iterating over the data till satisfy. So how we can iterate? We can do iterate by using three different types. We will say the number of times we want to iterate over data. Okay, so number of time we want to iterate over, that is one way of doing this. Okay, second way will be uh, you will say that okay, uh, maybe till the point of certain value of w that you want to achieve. Okay, okay, I don't remember the second point. Let's talk about third point right now. This is the second number of time I can achieve. Third point is when my loss function or accuracy is not changing, much. So that means based on the parameters I'm finding, and when I'm fitting the model, and I'm finding the difference between actual and the predicted one, and I'm finding that the updated value is not giving me much difference of the value. It's giving very minimal, like 0.00012 kind of thing. At that time I will stop. So that is the kind of thing. Second point I forget, maybe I will try to find and I will let you know. So this is a typical learning framework of any learning of any algorithm that you're going to learn in this course. Okay, now let's see how we want to uh, learn the algorithm. Okay, to give that, let's have another intuition. Now earlier we have seen in Perceptron that our data, when we are doing the loss function and we are finding the accuracy, and when we plot it, the accuracy part, we have find this kind of thing, this kind of model we have found, right? Like it has lot of up and downs with respect to it, and what we want was, we want the learning curve like this. Okay, so this is with respect to the accuracy we are talking about. What about the loss function? Loss function also, when we are going to plot a loss function, okay, for any number of epochs, instead of having this like this loss function, we should gradually decrease the loss function. Okay, so this is the loss function, and maybe this is the number of epochs you can assign to, or the parameters. So we should try to aim for this kind of aspect, where we will gradually improve the loss function, maybe using learning rate, using epoch, or the concept we're going to bring here is gradient descent. Okay, so that we're going to discuss now. So if you get an idea that how the typical learning algorithm looks like, and what is we are trying to achieve through that learning algorithm, what we are trying to achieve is this part. We are trying to achieve this part of loss function, the bottom corner, right corner I'm talking about. Okay, so let's go over here and try to see what we can have with respect to the learning function that we are having, with respect to the sigmoid. So the sigmoid function is again mathematical function. Let me write it down here. Is 1 plus 1 e raised to wtx plus b. Okay, this is a dot product kind of like that, and we want to find basically we want to find the values of w and b. So what we can do is, we will initialize w and b. Okay, we'll iterate over data. How? By computing by y bar, that is the fx function, the predicted function we are finding, because based on the w and b. Then we'll calculate loss function w and b. Okay, once you find the loss function, we'll find that values are we need to improve the loss. So what we'll do is, particular instance, we'll improve the weights by adding by subtracting, in this case, this n is the learning rate, and delta wt. What is delta wt? We'll talk about. And similarly for bt plus 1, that is at the t plus 1 instance, we will take the uh, value of b at the tth, ith, or tth iteration, and minus n is the learning rate in this case. And or you can, I forgot what this thing, this sign tells us, but, and the delta bt, whatever the difference we are trying to do. Why this delta? Because because what we want is, if our vector is like this, we want to slowly improve our relationship between w and x vector, like we have discussed earlier, right? So we want to slowly improve the relationship w between w and x. If you directly do this, the learning will be very random abrupted, because it will try to fit for a particular data point, but we want to fit for most of the data points. That's why the learning rate should be very minimal. So slowly look at each and every data point and improve the parameters of w and b accordingly. Okay, now okay, and again this intuition of, again the intuition of this, that is the learning what we computed earlier for w and b. We have to understand that whatever the new loss value we are going to get, it should be less than the old loss function, then only we can achieve this kind of curve, right? So our algorithm should be, or the this data point that we're talking about, let me highlight it, right? This parameter, the wt and the wbt, the delta wt and delta wt, it should be such that it is giving me better loss function compared to the old one. Okay, that is the our objective. And if you get till this point, now let's go little mathematically understanding that what and how the gradient descent actually work. Okay, so here the concept gradient descent will come, and let me remove this stuff. This, if as we discussed it, this is a kind of family of functions uh, of a sigmoid family of functions. So here the value of w and b will be deferred, and based on that we are getting different type of curves, right? Now let's assume that to, let's suppose that you have a data, or you have a points something like this. Let me do this like this, and you're starting with this data point, the black one. Okay, so I'm highlighting with red. Now this is from where uh, you started your line, and you want to go till here, the new line. That means you have to start off and you have to adjust the weights in such a way that it should move towards right hand side, and it should try to cover this spots. Okay, that's the objective that we are having, and that's the objective that the sigmoid neuron wants to achieve. So let's have it more clearer way. So this is the kind of similar kind of parameter learning, and what we try to do, we will try to guess it basically. So if you have something like start with 0 and this thing, and we want to achieve this, we want to cover fit this data point. Okay, so maybe at w0 and this, maybe we get a line kind of like this. Okay, now what we'll do, maybe I will improve w equal to 1 and b equal to 0. So then maybe let's say is 1, this is 1, this is 2. Okay, maybe I will improve little bit more, and then I will get this data point. So I will see that okay, my slope is well good, but only my value of b is not there, still it's very far. So maybe I will do w equal to 2, b equal to 0. So maybe I will go like this. Again I'm getting a much better equation of file, it is getting closer to 0. And maybe I will do then w equal to 2, maybe b equal to 1. So maybe I will go like this. Then I found that okay, I need to change this b, it became little bit more forward, so I will go w equal to 2 and b equal to 0.5, something like this, and maybe it can fit my data like that. Okay, so it is 2, 3, 4, and this is 5. Okay, now what we have done here is we try to guess the value of 0, b, and by changing the value of w and b, we are getting certain lines, and we try to see whether that line is equivalent to that or not. Okay, but the problem with this approach is how many different guesses you can do. There should be some principal approach with respect to this. Now once I'm doing this, obviously I can take a help of loss function, try to understand that, but still it is very computationally very extensive, because I might start at certain point of time, and just to reach there I might take a lot of time. Okay, because I need to I need to preserve this loss function directly like this also, right? So I should first to know that whether I'm the proper direction or that itself will take time, and after that to move towards that direction I should have some intuitive way. Random guessing work will not help me in this case, and in this case since we are showing it pictorially, then because I'm increasing the w value and b value of 111, it makes sense. But at actual training it might we are it's not that apparent that we need to increase the weight or decrease the weight. We should learn where to increase and where to decrease. That is something we should have some intuitive way with respect to that. There we will come the concept of gradient descent. So why the concept of gradient descent is actually coming to picture is, let's suppose the same algorithm that we have saw here. Okay, and this is a 3D version, maybe for two so same thing I'm posting with respect to wb and loss. Wb are my parameters and the loss function is there like this is a 3D plot. Okay, maybe I'm starting here at the some orange part of the this thing, and my actual value will be coming here somewhere the down, because it's the bottom pass, and the lesser the loss the better my model will be. Okay, that's we know. So what I want is that it should go directly like this rather than it will going like this, then it might go like this, again it will go like this, it will again. So it's a kind of zigzag minor, or it's a kind of random thing. But what I want is, no, I don't want that aspect. What I want is basically it will directly go towards the minimum value, towards that. So this is a kind of descent you're doing with some point value you're going and you're trying to find the minima. So this is called as minima. Maybe uh, you can say as local minima. Okay, so how do we do that? That's a question. So how do we tell that without going zigzag manner, which we can get it from guessing, I can directly go slow towards this direction and try to find the local minima in this case, or some case some inaccuracy you can find local maxima, but let's forget about that. Let's talk about this one, because we are talking with respect to loss function. Why loss function? Because loss function will tell us whether the model is doing good or not with respect to training data. To do that, we should understand a concept of, you should know something called as Taylor series. Okay, now what is Taylor series? Before going to that, how you're going to get a new loss function between w and b, how you can write it as is w new w dot delta w and b dot delta w, b dot delta b, like that. This is the actual way of doing it, because you're adding it. Now delta w can be positive, negative, that's a different question, but that's how we are going to see this. Okay, so we are focusing on this delta b, how what kind of values of delta b should be there. Okay, now this is for lw loss function we're talking about, and we know that L new of WB should be less than L old of WB. That is, our all the new loss function, the new value we are going to get from loss should be lesser than the older loss that we are going to get. Okay, so if this intuition is clear, what Taylor series will talk about is, it deals with the similar kind of expressions, that is f equal to x plus delta x. Now what here also we can try to see that how it is related to L new like this. So it is, we are dealing with the wx. So if improving on delta x, what kind of value we will get? So Taylor series will talks about fx, and then I'll just write it down the whole equation of the how it looks like for a Taylor series. Then we'll talk about. So I'm just going to give intuition, I'm not going to derive anything much here, but we'll get an idea of how it will actually look like. Now, if you can see this, I just exposed to the three equations. This is something called fx, then this is something called f dash of fx into delta x, and 1 by 2 1 by 2 factorial uh, double dax of x and x square. Okay, this is what we're talking, this is the Taylor look like. Now to get an intuition of this loss for with this, if you want to connect with the loss function, what you have to see is my this term, the highlighted red part, that is apart from fx, it should be negative. then only my fx dot delta x should be less than the fx value, because our aim is this only, right? It should be less than fx, because this is, we are dealing with the loss function here. Okay, so we want to achieve this part using negative x. And how do we achieve that? Here comes a picture of derivatives. Derivatives in this case of this f dash of x, f dash of x will basically a derivative of function fx. So if you know under derivation, so it will be like d by dx by fx. In terms of loss function, we will write it as dl of lwb. This will be partial by w, or lwb by partial by b. So this is the partial derivatives that we are talking about, because we have two parameters. Fx, if you have only one parameter, is a typically derivative. So if you know this concept, that is it's okay. If you don't know, the gist is what, that what we are trying to find is, when we are trying to expand our loss function, what we are finding this, the derivative of the loss functions, in this case the this values that we are talking about, the bottom up where we have wrote the partial derivative equation, this value should be negative. If these values are negative, then I can say that whatever the upgradation I'm doing with the loss function, it is actually lesser than the L old. I hope you're getting this aspect with respect to this. Uh, Again, if I want to write is w, if suppose let's say w as the only parameter for loss function, it should be, the new loss function should be less than new loss function should be lesser than the old loss function. So w is already available, so we can't change that. But what we are changing is parameter n, learning, this is a learning parameter. Learning parameter will be always positive, so we can't change this. So only thing we can change is delta w, and this delta w is basically a derivative. Okay, and derivative is basically, in this case, we're trying to make it as negative. And how we can make it negative? Here the concept of, again, the angles between angle between w and x will come into picture, and what we're trying to say is, we're trying that this w value in this case will always be negative, such that it will always go away from the x parameter in this case, for certain cases only, and try to see that how my relationship between wx, such that it will go down and down, such that the delta value in this case will be negative and my loss will be decreasing. uh, this is a kind of intuition it's all about. Obviously this is a very big derivation with respect to how it can do, but I hope you can understand that this is what we are focusing upon, the new loss function, and here we are dealing with a delta w, and this delta w will be, actually we talks about as the gradient descent. Descent is coming from the value, that because this value should be mostly will be negative, because we want to use the loss function with respect to that. Okay, now once we get this also, the the value of this this part will reduce the weights, or will reduce or increase the weight according to the instances, but it will do that so that our loss function will reduce. Now all this thing of which we call as derivatives or Taylor series, if you're not interested, that is totally fine with us with mathematical intuition. But all this thing you don't need to think much about during the implementation part. Why? The implementation part will just say that find me minimum of wb, given that my loss function is wb, and this loss function will be like, find me minimum of wb, and my loss function is square function. So it will automatically, the PyTorch or the TensorFlow, so whatever the Taylor series and the derivatives I'm telling right now, it will calculate and it will try to find the minimum value of w and b, such that my loss function will be minimum, and it will do automatically, these things will be do. But you should know that why the some aspect of what it is actually doing, how it is actually updating, right? And this is a kind of common thing in all the other backpropagation methods or backpropagation of CNN as well, where you're trying to reduce the loss function by updating the value of W in such a way, mostly in such a way that you're trying to find the local minima within the loss function when you're trying to plot W and X and W and B in the 3D scale. Okay, you're trying to find the local minima point here. Okay, so only the so I hope you get the understanding of the learning function here. The only part remaining is how you evaluate. So evaluation is again to evaluate a sigmoid neuron. To evaluate a sigmoid neuron, you can, for classification you will use accuracy, I think, which is pretty evident by this time. And there is something called as, for regression, it is RMSE, that is root mean square error. That is will look like root mean will be I to n y minus y square. For each point it will try to find it's basically, this is a loss function itself, but you're just putting a root over that. So this is the kind of, this value will give you the how the model is. So the, if the value, it is the lesser the value, so RMSE, less value, good performance, okay, and high value, bad performance. So we want to reduce this because eventually it is related to loss function itself. So the higher the value of RSME, it's not good for us. We need to improve the model. Okay. Okay. So that's the end from my side with respect to sigmoid neuron. The reason the some mathematical intuition I've tried to brought here is to tell you that if you try to plot the parameters, in this case WB, but in other algorithms it might be more parameters will be there, and we will try to plot that with respect to loss function, what you're trying to aim and what is actually happening in the behind, which you don't know because you're directly going to use a function that it is trying to find a local minima when you try to plot this whole graph, okay, such that your loss will be minimized. And to do that you use the concept of gradient descent, where whatever the delta W and delta B value you're getting, you're trying to reduce, you're going to add that on the original weight parameters and try to see that how you can reduce the loss function. That is what the crux of the last 1 hour that we are going to that we have discussed with the sigmoid neuron. Okay, so if you have any question, please let me know. If it is went over you, that is, I want you to please look at the lectures one more time, because this is very important for you to understand, because it's very easy for you to maybe just go and apply loss function just and it will calculate automatically, but why it is calculating, is this something you should understand properly. So that is my motivation with respect to this. So that's the end from my side. If you have any question, please let me know. So from next week, we will again go back to the, maybe look at some assignment questions, and we'll go back to coding of backpropagation technique, which is the first model that we are learning right now.
So we will see all this theoretical aspect which you explained just now in the next session in the coding part.
See, we can go ahead with that, because this itself will, if I want to explain the whole mathematical derivative with respect to it, will take 2 hours for me to just to explain how it is going to happen, because this, we can play with how this Taylor series are actually linked with it. I haven't shown it, I just told you overview of that, because many of the people are not interested in that. But if you want, I can upload a video separately where I'm just going to explain that how the derivative of Taylor series is actually leading to finding the gradient descent. But mathematically, I think most of the people might not understand it.
So it will be better if you go for both the things, the mathematical as well as the coding part.
Okay, maybe I try to balance it such that I might not go into too much of derivative like today, but I will try to give you intuition that why the certain things are happening in a certain way. So I will take care of that as well.
Okay, sir. Thank you so much.
Yeah. Is there any other question? Okay, so in that case, I am stopping the recording, and um,